Welcome to Dr. Sherry's Astronomy channel. The topic of this episode is discovery of a future Earth orbiting a dying star. When a star evolves and reaches the end of its life, it has a significant impact on the planets around it. In the case of massive stars, during their final stage, they undergo a supernova explosion, and the enormous energy and shock waves released during the explosion are expected to destroy the surrounding planets. On the other hand, relatively lighter stars like the Sun will expand into a red giant as they approach the end of their life. In the red giant phase, the star begins to shed its outer layers, and gas and dust shells expand outward, surrounding the star. These expelled gases and dust glow due to the intense ultraviolet radiation from the hot core at the center, which is transitioning into a white dwarf. This results in the formation of a beautiful planetary nebula, which is observed. A planetary nebula is a temporary phenomenon that occurs during the process of white dwarf formation and lasts only for a few thousand years. Afterward, the gas disperses and disappears, leaving only the central white dwarf behind. When considering the evolution of a Sun-like star, planets around it are thought to be destroyed during the red giant phase. However, theoretical research suggests that planets located between 1 and 3 astronomical units away may avoid such destruction and survive. An astronomical unit is the distance between the Earth and the Sun, so Earth might survive without being destroyed. On the other hand, in the search for exoplanets, the discovery of planets orbiting red giants and white dwarfs is extremely rare. Recently, a research team led by Dr. Zhang from the University of California used gravitational microlensing to discover a white dwarf with 2 small companions, a planet of Earth's mass and a brown dwarf. This discovery offers a glimpse into the future of Earth. Let's take a look at this discovery through the lens of microlensing. Gravitational microlensing is a type of gravitational lensing based on Einstein's theory of general relativity. A massive object distorts spacetime, causing light from a background object to bend as it passes through the distorted spacetime. As a result, the observer sees the light from the object as brighter, or the shape and position of the object may appear distorted. This phenomenon is called gravitational lensing. Gravitational lensing has 2 effects: the magnification effect, where the background object becomes brighter, and the distortion of the image, where the shape and position change. The magnitude of these effects depends on the mass of the lensing object and the relative positions of the lensing object, background object, and observer. In particular, when the lensing object is very massive, and the background object and observer align in a straight line, a strong lensing effect can occur, sometimes appearing as an Einstein ring. Gravitational lensing is caused by any object with mass, but when a light object causes lensing, the angle by which the light bends is extremely small, making it difficult to capture the lensing effect in images. For example, a star with the mass of the Sun bends light at an angle of about 0.8 milliseconds. This is a very small angle, almost equal to the resolution of ground-based telescopes. Even if the image distortion is not observable, it can be detected as a temporary increase in brightness. This phenomenon is known as gravitational microlensing. One key aspect of observing gravitational microlensing is that the lensing object, the background object, and the observer are all in motion. For example, when a single white dwarf passes close to a background star along the observer's line of sight, the motion of the white dwarf increases the gravitational lensing effect, and when the white dwarf moves away, the effect weakens. This motion causes the background object to appear much brighter due to the lensing effect. By observing this gravitational microlensing effect, it is possible to measure the mass of an object that cannot be directly observed. The Earth-mass planet orbiting the white dwarf was confirmed during a microlensing event that reached its peak brightness in July 2020. The brightness change looks like this. The horizontal axis represents time, and the vertical axis represents the brightness in magnitude. The data obtained from various telescopes is shown. At first glance, It seems like a typical microlensing event caused by a single lensing object, but when you zoom in around the peak, you can see that the event involves more than one object. For example, the zoomed in portion shows the magnification and dimming phases. The black dotted line represents the model for a single lensing object. The light blue line represents the case of a binary system as the lensing object. The gray line represents a triple system, indicating a three-body lens system. This light curve shows that the model with a single lensing object is rejected. Further zooming into the peak of the light curve, the models remain the same as before. The binary system model is rejected, and it is clear that the lensing object is a three-body system. This system involves an Earth-like planet and a brown dwarf orbiting a star smaller than the Sun. A brown dwarf is an object located between a star and a planet. It lacks the mass required for nuclear fusion like a star and cannot emit light like a normal star. The models also suggest that in some cases, the brown dwarf is close to the main star, while in other cases, it is far away. All models agree that the Earth-like planet is located between 1 and 2 astronomical units from the star. Thus, the mass and distance from the main star resemble those of Earth. While we can determine the characteristics of the planet, the microlensing analysis alone couldn't identify the specifics of the main star. Without mass data, it's impossible to tell whether the main star is a normal star like the Sun or an evolved remnant such as a white dwarf. To resolve this, the research team used the Keck telescope in Hawaii to identify the main star. White dwarfs, remnants of stars like the Sun, are much dimmer than normal stars on the main sequence. By measuring the brightness difference, the team could distinguish between a normal star and a white dwarf. The team used a laser guide star to correct for atmospheric turbulence, obtaining high-resolution images to separate the main star from the background star that acted as the microlensing source. From this analysis, they determined that the brightness was coming from the background star and not from the lensing object, indicating that the lensing object was very dim. As a result, the team concluded that the main star in this triple system is a white dwarf, not a normal star. Building on this, the research team reanalyzed the microlensing data. They found that the masses of the three objects in the system were as follows: the Earth-like planet is about 1.7 to 1.9 times the mass of Earth, the brown dwarf is about 30 times the mass of Jupiter, and the white dwarf, the main star, is about 0.5 times the mass of the Sun. The Earth-like planet is located about 2.1 astronomical units from the main star. The research team also proposed a model for the evolution of this triple lens system. When the main star, which eventually became a white dwarf, was still on the main sequence, the planet orbited close to it, while the brown dwarf existed on a more distant orbit. At this point, the main star, planet, and brown dwarf were all bound by gravity, maintaining stable orbits. As the main star evolved into an old AGB star, asymptotic giant branch star, it shed large amounts of gas, losing mass. This mass loss changed the gravitational balance, causing the orbits of the planet and brown dwarf to expand. During this phase, the brown dwarf and planet remained stable, avoiding interference with each other. As time went on, the star's mass continued to decrease, and the orbits of the planet and brown dwarf continued to widen, eventually forming the final triple system. In this way, a stable distance between the three bodies was maintained, resulting in a triple lens system. In conclusion, the planet discovered in this study may have originally had an orbit close to 1 astronomical unit, similar to Earth. As the star evolved, the planet likely moved to its current position. This model of orbital migration offers new insights into the future of our solar system, especially regarding whether Earth can survive the Sun's final expansion. While Earth may be swallowed by the Sun as it evolves into a red giant, there is also a possibility that the planet will survive by expanding its orbit, just as in this triple system. This system serves as a perfect example of that scenario. So, Could life survive on Earth if it does endure? Even if Earth's orbit stretches as far as this discovered planet's, the expanding sun's heat would likely cause the oceans to evaporate, and eventually, the surface would be covered in molten lava, making Earth a scorched planet. Thus, it would be difficult for life to continue as we know it today. However, as the Sun evolves into a red giant, the habitable zone could extend to the orbits of Jupiter and Saturn, and many of their moons could become ocean worlds, capable of sustaining life. If that happens, humans may be able to relocate there. This change is expected to occur in about 1 billion years. By then, humanity may have developed solutions to survive.
この動画をご覧になって、面白かったらチャンネル登録と高評価をよろしくお願いいたします。また、発信の機会を増やすために、旧 Twitter、X と Instagram も活用しています。よろしければ、こちらのフォローもお願いいたします。